Hi, I appreciate your time a lot. Today we're going to be talking about pulmonary function test, specifically spirometry. Don't worry if you have found these graphs very confusing in the past. I will try to do my best, break it down and make it easy to understand. And I hope that by the end of the discussion, you should be able to confidently interpret pulmonary function test and identify any potential pulmonary function abnormalities. So go ahead and support me. Hit the subscribe button for more insightful discussions like this. Let's get started. So what's the purpose of a pulmonary function test? When do you recommend it? To distinguish between obstructive pulmonary disorders such as asthma, COPD, and restrictive conditions like pulmonary fibrosis. PFTs also help assess the severity of lung impairment, and additionally, PFTs are vital for assessing the effectiveness of treatment. It's important to say that in the evaluation of restrictive pulmonary disorders, reliance solely on PFTs are not encouraged, and other imaging modalities like CT scan may be indicated. All right, so here we're going to take a practical approach to understanding this illustration. All right, let's begin by breathing in and out, in and out, just as you will during your restful moments. Okay, we're going to call that tidal volume, which is approximately 500 mils. All right, now from this point here, which is the end of expiration in the tidal volume, taking a deep breath such that you cannot inhale any further. We're going to call this inspiratory capacity. From the inspiratory capacity, breathe out quietly all the way down to this point here. I said breathe out quietly, right? So we're going to call this vital capacity. Recall that there is a certain amount of air in the lungs that we can never get out, which ensures that the lung is not completely empty. We're going to call that your residual volume, which is also about 1 liter. Now, we could actually take the curve all the way back to the inspiratory capacity. And this time, we're going to breathe out forcefully or rapidly to the utmost extent. Okay, so we're going to call this forced vital capacity. So looking at this, what is the difference between your vital capacity and forced vital capacity? Well, the answer is forced, because in FVC, the air is forced out. In VC, the air is blown out quietly. That's the difference. During the FVC test, the computer spirometer effectively measures 1 second of the FVC. So we're going to call that forced expiratory volume in 1 second, which is a very good parameter for assessing obstruction, right? If you have any obstructive disease like asthma or COPD, you cannot bring the air out, then this parameter is going to decline. Now let's make some further deductions. Now, aside the tidal volume, we still do have the capacity to breathe in. And so we're going to call this your inspiratory reserve volume. All right, very important. Now, you can see from the graph that if we combine the tidal volume, okay, that is from here all the way down to this part here, then we have the inspiratory capacity. So inspiratory capacity is equal to your IRV, which is your inspiratory reserve volume, plus your tidal volume. Okay, now we can also take a breath out aside the tidal volume. And so we also have a reserve, and that's going to be called your expiratory reserve volume. If you combine the residual volume with this expiratory reserve volume like this, we get something known as functional residual capacity, which should not be confused with the forced vital capacity. Okay, so this is our total lung capacity. So we can say that the total lung capacity is equal to the residual volume plus the ERV which is your expiratory reserve volume plus the tidal volume plus your IRV. Okay, and then you recall that if you put these two together, that is your residual volume and the expiratory reserve volume, you get what? You get the functional residual capacity. Plus, if you put the tidal volume plus the inspiratory reserve volume, you get the inspiratory capacity. So this is the total lung capacity. Okay, a formula to understand. So it's very important that you understand this curve because based on the ratio between that is F E V in 1 second over the forced vital capacity, we are in fact able to distinguish between obstructive and restrictive disease. So in short, let me write here, O is for obstruction, R is for restriction. And so in obstruction, this ratio is usually less than 0.7. And in restrictive diseases, this ratio is preserved within the normal range or is beyond 0.7. All right, so here we're going to analyze 3 spirograms to enhance our understanding, okay? So let's take a look at the first one. So let's say that we have a tidal volume right here. Okay, then we have an inspiratory capacity that goes all the way like this. That is the forced vital capacity to this point. Okay, so this is the tidal volume. That's about 500 mils. This part here is going to be the inspiratory capacity, which is about 6 liters. This part here, what do you think this is? This is the residual volume. That's about 1 liter. Okay, and if we know that this box is 1 second, then from all the way here up to this part is going to be the forced expiratory volume in 1 second. So this part here is going to be the forced vital capacity. All right, so if we try to come up with the ratio, then we're going to have FEV in 1 second over FVC. So FEV1 is about 4 liters over FVC, which is about 5 liters. And putting this together, you have about 0.8, which is more than 0.7. So this is a normal spirogram. Okay, let us take a look at the second one that I'm going to draw. So let's say here we have a tidal volume, right? And then something like this. Then what you see is that this graph seems to have a shift actually to the left. Okay, I will explain that. So again, we have a tidal volume somewhere here, which is 500 mils anyway, but then we see that the total lung capacity has increased. If here it was at 6 liters for inspiratory capacity, here we are having 7 for the inspiratory capacity. Okay, again, if we take a look at this down here, this is the functional residual capacity, which seems to be elevated as well, increased. And this is the residual volume, which is also increased. So if we take this part here as the forced expiratory volume in 1 second, and this part here as the forced vital capacity, then we could actually say that we're going to have 2 liters over 4 liters, okay, which is giving us about 0.5. Obviously, this is less than 0.7, and this seems to be an obstructive parting. Okay, now let's take a look at the third one. So here we have, most likely it's going to be the restrictive type, right? So we do have the tidal volume, say somewhere here. Okay. And then we're going to have something like this. So obviously, we see that the curve is shifted to the right. The residual volume is pretty much reduced, very small. The functional residual capacity is also reduced. And if this is the forced expiratory volume in 1 second, then this is going to be the forced vital capacity as well. So that if we divide, I think we have something around, say, 3 divided by around 3.5. Okay, and obviously this is more than 0.7, and so this looks like a restrictive pattern spirogram. All right, so think of any restrictive disorder like pulmonary fibrosis where the lung is shrunken and there is loss of volume. Okay, so volume loss means that the lung has also lost vital capacity. Now think of a lung that has lost volume and has a small vital capacity. Will that lung be able to force air out? Certainly no. So the forced vital capacity is also substantially declined. In fact, restrictive lung disease does not necessarily mean an obstruction. Hence, FEV in 1 second may actually be reduced, but the FVC is substantially or considerably reduced, hence making the ratio greater than 0.7. On the other hand, if we take a look at an obstructive lung disease, okay, the volume is either normal or even bigger, okay, because there is entrapment of air in obstructive lung diseases. So vital capacity may remain the same. Hence, in obstruction, okay, the point is that you're certainly not able to bring air out. So the forced vital capacity is decreased, but it is not as substantial as the air you bring out in 1 second. So that is significantly reduced. So we're going to have a ratio that is the FEV in 1 second, which is substantially or considerably reduced compared to the FVC, which is reduced. And so this gives this R ratio less than 0.7 for obstructive lung disorders. In this section, you are seeing the normal predictive values. It is equally important to identify when we can classify airway obstruction as reversible. To do this, we give a bronchodilator such as salbutamol and subsequently reassess the patient's FEV1. If there is an increase in FEV1 by 12% from the baseline or an increase of 200 mL, we conclude that the criteria for reversibility has been met. It is crucial to note that unlike obstructive disorders, restrictive disorders do not show reversibility. All right, so what we are observing is a flow volume loop that is a graphical representation of airflow during the breathing cycle. So what I have here is inspiration, and on top I have expiration. And the process does not begin at 0 simply because of residual volume. So from 0 all the way to 1, we're going to have our residual volume, which is normally around, say, 1 liters. Okay. So on inspiration, what happens is that we start to breathe in and we increase the volume of the lungs all the way to, say, 6 liters, which is going to be the inspiratory capacity. So we could actually say that the distance from here to this part is going to be the vital capacity. All right. And the process will shift to expiration where the lung volume will decrease. And so this is a normal flow volume loop. Now let us compare this with a patient who has an obstructive lung disease, for example. So in this disorder, we see that the residual volume is actually increased significantly, for example, all the way to, say, 2 liters. So this residual volume is increased in obstructive lung disease. So the flow volume loop is going to start from somewhere, say, 2, and it's going to go all the way like this to, say, this part here. For example, 7 liters. Why? Because the total lung capacity increases in obstructive lung disease. And there is also a problem with the flow of air during expiration. So the diagram or the curve doesn't go too far, and it's going to get back to its original position. So what we see is a shift actually to the left. Okay, now let us compare this again with a patient who has a restrictive lung disease. So those type of patients certainly have a decrease in the residual volume. So residual volume in restrictive lung disease decreases, right? And so the diagram is going to start from somewhere, say here, and goes all the way to, say, 4. So this is going to be the inspiratory capacity, which has actually decreased, all right? And they can also have a decrease in flow during expiration. So that the curve is going to be something like this. There is a shift to the right for patients with a restrictive lung disorder. Now, again, on the same diagram, we are actually seeing a graphical representation of the forced vital capacity in time, okay? And normally the forced vital capacity, if this is the forced vital capacity, the forced expiratory volume in 1 second will be about 80% predicted. So in a patient who has an obstructive lung disease, okay, what can happen is that they can have a graph like this. And so the forced expiratory volume in 1 second will decrease, okay? And the forced vital capacity would also decrease. Now let us compare this to a patient who has a restrictive lung disease. They can actually have a much more fixed forced vital capacity. So they can have a diagram like this, okay? And so we see that the forced vital capacity is decreased for the patient with restrictive lung disorder. Diffusion capacity using carbon monoxide is valuable and a reliable component of pulmonary function test. It measures how effectively oxygen and carbon dioxide are exchanged between the lungs and the bloodstream. And this is how it is performed. You inhale air that contains a small amount of carbon monoxide and a tracer, such as helium. You hold your breath for 10 seconds. You then exhale the air out rapidly, and here we determine the quantity of tracer that was absorbed upon inhalation. So let's say you did a pulmonary function test and you have a restrictive pattern such that you have the FEV in 1 second to FVC ratio being greater than 0.7, and then you see that there is a decline or a reduction in the diffusion capacity, then you are most likely dealing with an interstitial lung disease. On the other hand, if you see a ratio which is less than 0.7 with a decline or a reduction in the diffusion capacity, we are most likely seeing an emphysema. Thank you, and I hope this was useful. If you enjoyed it, then hit the like button and subscribe to the channel. Bye.